Hello there, and welcome to Sleepy Science Vault. When we look up at the night sky, we see stars, planets, distant galaxies, light scattered across an ocean of darkness. And it's natural to assume that everything between those glowing points is simply nothing. Just emptiness. A blank and featureless void stretching on forever. But the universe is rarely as simple as it first appears. The space between stars, between galaxies, between everything we can see, it isn't truly empty. It only looks that way. And the difference between empty and nearly empty turns out to be one of the most fascinating distinctions in all of science. What we call the vacuum of space is technically known as a hard vacuum. It contains extraordinarily little matter, far less than anything we could ever recreate here on Earth. Even our best laboratory vacuums still hold billions of particles per cubic centimeter. Space, on average, contains just one atom per cubic centimeter. Across the vast stretches between galaxies, that number drops even further, sometimes to less than a single atom per cubic meter. To put that into perspective, imagine a small dice sitting on a table in front of you. If that cube were filled with the average density of outer space, it would hold somewhere between 1 and 2 particles of matter. Not molecules. Not clusters. Just 1 or 2 lone particles, drifting in silence. And yet, that dice-sized cube of space is practically crowded compared to what lies between galaxies. Intergalactic space, the immense dark distances separating one galaxy from another, is hundreds of times emptier still. Out there, you could travel for extraordinary distances without encountering a single atom. We reach the edge of Earth's atmosphere and cross into what we call space at around 100 kilometers above the surface. That invisible boundary is known as the Kármán line, and it's the point where the air becomes so thin, so diffuse, that it no longer behaves like air at all. The atmosphere simply fades. And beyond it, the silence begins. Because space is completely silent. Not quiet in the way a forest is quiet at night, with subtle sounds underneath the stillness. Truly, absolutely silent. Sound requires molecules to travel through, vibrations pass from one particle to the next. But in a near-perfect vacuum, there are no molecules close enough to carry that signal. Every explosion, every collision, every star that has ever erupted in distant fire, all of it happening in total, unbroken silence. And this vast, near-empty silence is not staying still. The universe is expanding. Every moment, the space between galaxies is growing wider. Not because matter is flying outward from some central point, but because space itself is stretching, the fabric of everything gently, continuously pulling apart. The distances involved are almost impossible to hold in the mind. The universe isn't just large. It is so large that even the emptiness has a scale that defies imagination. And within all of that emptiness, all of those impossible distances and near-zero densities, the matter that does exist, the atoms, the particles, the lone wandering hydrogen molecules drifting in the dark, feels all the more remarkable for being there at all. Empty space is really almost empty. Almost, but not quite. And as we'll discover, that tiny almost changes everything. So if space isn't truly empty, If even the quietest regions of the universe contain something, then the question becomes, what, exactly, is out there? The answer begins with something called the interstellar medium. It's a term that sounds almost bureaucratic, clinical even, but what it describes is anything but. The interstellar medium is the material that fills the space between stars, a diffuse, sprawling mixture of gas and dust that permeates the entire galaxy. It isn't visible to the naked eye. It doesn't glow or sparkle under ordinary light. But it is there, woven through the Milky Way like an invisible atmosphere, present in every direction we look. And it's not a small thing. Despite being extraordinarily thin and spread across unimaginable distances, the interstellar medium accounts for roughly 5% of the total mass of our entire galaxy. 5% might not sound like much, but when the object in question is the Milky Way, containing hundreds of billions of stars, 5% is a staggering amount of material. Quietly filling the spaces between everything we can see, largely unnoticed, is a sea of gas and dust that outweighs entire civilizations of stars. The dominant ingredient in that sea is the simplest element in existence: hydrogen. The very first atom to form after the Big Bang, and still, billions of years later, the most abundant substance in the known universe. By mass, roughly 75% of all the visible matter in the cosmos is hydrogen. Most of the remaining quarter is helium, the second lightest element, almost as ancient, almost as simple. Together, these two elements make up nearly everything we can detect. What's remarkable is that hydrogen and helium don't exist out there in just one form. In the cold, quiet reaches of space, hydrogen drifts as neutral atoms, complete, stable, unhurried. But closer to stars, where intense radiation floods outward in waves, that hydrogen gets stripped of its electron. It becomes ionized, electrically charged, reactive, a slightly different version of itself depending entirely on where in the galaxy it happens to find itself. The same element, behaving in fundamentally different ways depending on its surroundings. Space, even in its quietest regions, is constantly shaping the matter within it. But hydrogen and helium alone don't tell the whole story. Because when you look at Earth, at the iron in your blood, the calcium in your bones, the silicon in the ground beneath you, none of that came from the Big Bang. Those elements didn't exist in the early universe. They had to be made. And they were made inside stars. Everything heavier than helium, every carbon atom, every oxygen molecule, every trace of iron or gold or uranium, was forged in the nuclear furnaces at the hearts of stars across billions of years of cosmic history. The process is extraordinary. Stars spend their lives fusing lighter elements into heavier ones, building up layer by layer through their long, slow burning. And when those stars reach the end of their lives, when the largest ones collapse and detonate in the violence of a supernova, they scatter everything they've built outward into space. The heavier elements, the ones astronomers collectively call metals even when they aren't metallic in any familiar sense, make up only about 2% of the visible universe's total mass. Just 2%. And yet within that 2% lies the entire periodic table beyond helium. Every element that makes complex chemistry possible. Every element that makes planets, oceans, atmospheres, and life possible. 2% of the universe contains everything interesting about it. Stellar winds carry these elements outward during a star's life, a slow and continuous shedding of material into the surrounding space. And when a massive star dies in a supernova, the dispersal is sudden and violent and magnificent, a shock wave of enriched material expanding outward at thousands of kilometers per second, seeding the interstellar medium with the raw ingredients for whatever comes next. For new stars, new planets, new chemistry. We are, in the most literal sense, made of this material. The atoms in your body were forged in stellar cores that exploded long before our solar system existed. But that connection to the cosmos isn't just poetic history, it's ongoing. Every single day, Earth receives a quiet delivery from space. Cosmic dust, fine particles drifting through the interstellar medium, falls continuously into our atmosphere. Some of it burns up on entry as the tiny meteors we see as shooting stars. Some of it floats gently down and settles onto the surface of the planet. Thousands of tons of extraterrestrial material arrive on Earth each year, so fine and so spread out that we rarely notice it. It lands on mountains and oceans and rooftops and fields. Ancient stardust, carried across the galaxy over billions of years, finally coming to rest on the same world where you're listening to this right now. The space between stars is not empty. It is an ocean, thin beyond imagination, yes, but rich with history. Filled with the raw material of everything that has ever been built in the universe, and everything that is still waiting to be. There is something almost meditative about dust. Here on Earth, we sweep it away, wipe it from shelves, watch it drift through beams of afternoon light. It feels like the residue of things, the leftover trace of life being lived. But in space, dust is something else entirely. In space, dust is a beginning. The interstellar medium isn't just gas. Woven through that vast ocean of hydrogen and helium are tiny solid particles, grains of matter so small they make the finest powder on Earth look coarse by comparison. These are the grains of cosmic dust, and they are built from some of the most fundamental materials the universe produces. Carbon, in various forms, graphite, amorphous carbon, the kind of carbon that in other circumstances forms diamonds. Silicates, the same mineral family that makes up much of the rock beneath our feet. Metals, carried outward from the cores of dead stars. And in the colder, quieter regions of space, thin coatings of ice, water, ammonia, methane, frozen around the surface of each tiny grain like a delicate shell. Each of these particles is extraordinarily small. We're talking about grains measured in micrometers, a fraction of the width of a human hair. And yet, collectively, they shape the universe in ways that are difficult to overstate. One of the most striking properties of cosmic dust is its relationship with electromagnetic fields. These grains are not passive. They respond to the magnetic fields that thread through space, aligning themselves along those invisible lines of force. When astronomers study the polarization of light coming from distant stars, the way the light waves are oriented as they travel toward us, they can actually use that information to map the magnetic structure of the galaxy. Tiny grains of dust, drifting in the dark, quietly tracing the shape of forces we cannot see directly. But perhaps the most profound role that cosmic dust plays is chemical. Out in the cold reaches of interstellar space, individual atoms rarely meet. The distances are simply too great, the motion too slow, for chemical reactions to occur easily between floating gas particles. Dust grains change that. Their surfaces act as landing pads. Atoms of hydrogen, oxygen, carbon and nitrogen drift through space, settle onto a dust grain, and suddenly find themselves close enough to react. The grain acts as a catalyst, bringing together ingredients that would otherwise never meet. This is how some of the most complex molecules in space are born. Amino acids, alcohols, sugars, organic compounds of startling complexity have been detected in the interstellar medium, many of them assembled on or near the surfaces of dust grains. The chemistry of life doesn't begin on a planet. It begins, quietly and slowly, in the space between stars. And there's one more state of matter worth considering here, because space contains something that doesn't fit neatly into the familiar categories of solid, liquid, or gas. It contains plasma, and not just the clean, simple plasma of ionized hydrogen near a star, but something stranger and more textured. Dusty plasma. A plasma that contains charged dust grains suspended within it, particles that carry electric charge and interact with the surrounding electromagnetic environment in complex, sometimes beautiful ways. Dusty plasma forms in the regions around dying stars, in planetary rings, in the wakes of comets. It's a state of matter that took scientists some time to fully appreciate, and it remains an active area of research today. Now, when we pull back even further, beyond individual stars, beyond the Milky Way itself, we reach the intergalactic medium, the space between galaxies. And for a long time, astronomers assumed this was the simplest region of all. If the interstellar medium within a galaxy was already thinly populated, then surely the vast emptiness between galaxies must be the purest thing in the universe, nothing but the original hydrogen and helium left over from the Big Bang. Primordial. Untouched. Chemically featureless. That assumption turned out to be wrong. As observational technology improved and astronomers developed more sensitive ways of studying the faint signals coming from across the universe, a different picture began to emerge. The intergalactic medium, it turns out, isn't primordial at all. It has been enriched. It contains metals, heavier elements that could only have been created inside stars, scattered across the spaces between galaxies by something powerful enough to carry them there. That something is galactic winds. When a galaxy undergoes intense star formation, the combined energy of countless stellar explosions and the radiation pressure from massive young stars can drive enormous outflows of gas and dust outward from the galaxy itself. These winds don't just stir things up within the galaxy, they can push material completely beyond its boundaries, out into the intergalactic medium, enriching it with the chemical products of stellar evolution. Galaxies, it turns out, are not sealed containers. They breathe outward, exhaling enriched material into the space around them over billions of years. The dust density out there is extraordinarily low, something on the order of 1 grain per million cubic meters of space. That is a level of emptiness so profound it barely registers as anything at all. And yet it's there. Even the deepest, most isolated reaches of intergalactic space contain traces of the universe's chemical history. How do we know? Much of the evidence comes from quasars, extraordinarily luminous objects at the hearts of distant galaxies, powered by supermassive black holes consuming vast amounts of matter. Quasars shine so brightly that their light can travel across billions of light years and still be detected by our telescopes. And as that light travels toward us, it passes through the intergalactic medium. Different elements absorb light at specific, characteristic wavelengths, a fingerprint unique to each element. By carefully analyzing the spectrum of a quasar's light, astronomers can read the chemical signatures left behind by everything that light passed through on its long journey. It's a remarkable technique. A beam of ancient light, generated billions of years ago at unimaginable distances, carrying within it a detailed chemical record of the space it crossed. Astronomers spread that light into its component wavelengths, look for the telltale absorption lines, and piece together the composition of gas clouds they could never otherwise study directly. What they found in those spectra reshaped our understanding of the universe's structure. Carbon, oxygen, silicon, elements that had no business being between galaxies, that had to have been forged inside stars and then expelled outward by galactic winds, were there in the data, encoded in the light. The dust between the stars is not an afterthought. It is not mere debris. It is a record keeper, a catalyst, a carrier of chemical complexity from one corner of the universe to another. And even in the most remote, most isolated regions of the cosmos, traces of that dust find their way, silently enriching the emptiness, slowly preparing the universe for whatever it intends to make next. Most people, if asked to name the states of matter, would say three: solid, liquid, gas. It's one of the first things we learn about the physical world: the ice, the water, the steam. A simple and satisfying progression from one form to another. But there is a fourth state. One that most of us were never taught about in school, despite the fact that it makes up the overwhelming majority of everything we can see in the universe. It is called plasma, and once you understand what it is and where it exists, the universe begins to look like a very different place. Plasma forms when matter is heated to such extreme temperatures that electrons can no longer stay bound to their atomic nuclei. The atom, that stable, complete structure we picture in chemistry diagrams, simply comes apart. What remains is a soup of free-moving charged particles, nuclei carrying a positive charge, electrons carrying a negative one, all moving independently, all responding to electromagnetic forces in ways that neutral gas simply cannot. It isn't a gas anymore. It's something fundamentally different in behavior, in structure, and in the role it plays in the universe. And the universe is absolutely filled with it. Roughly 99% of all visible matter in the cosmos exists in the plasma state. Stars are plasma. The solar wind streaming outward from our sun is plasma. The vast glowing clouds of ionized gas that astronomers photograph in stunning color, the nebulae, the remnants of supernovae, the regions around young stars, all plasma. We live, in a very real sense, in a universe made of plasma, with small islands of cooler, denser, more familiar matter scattered through it. The plasma closest to home is the solar wind, that constant stream of charged particles the sun breathes outward in all directions. It fills the entire solar system, pressing against the magnetic fields of planets, stretching and shaping the tails of comets, and eventually thinning out until it mingles with the broader interstellar medium far beyond the outer planets. But the most extraordinary plasma in the universe isn't found anywhere near a star. It's found in the spaces between galaxies. Intergalactic space, which we might instinctively imagine as cold and still, is in many regions anything but. The intergalactic medium contains gas heated to temperatures of millions of degrees, temperatures so extreme that the thermal energy involved is almost incomprehensible when set against the cold vacuum we imagine space to be. At these temperatures, matter emits X-rays. Not visible light, not infrared warmth, but high-energy X-ray radiation, the kind that can pass through solid objects. The kind we use in medical imaging. Diffuse, low density, but genuinely, measurably there. For a long time, this posed a significant puzzle for astronomers. When they added up all the ordinary matter they could account for in the universe, matter in stars, in galaxies, in the gas clouds they could observe directly, it didn't match the theoretical predictions. Roughly half of all the normal matter that should exist, according to our best models of the Big Bang and the early universe, was simply unaccounted for. It wasn't where astronomers expected to find it. It took decades of searching, and ultimately the development of sensitive X-ray space telescopes, to find where that missing matter had gone. It was in the intergalactic medium all along, hidden in a diffuse, extraordinarily hot plasma that came to be known as the warm-hot intergalactic medium, the WIM. Despite its somewhat unglamorous acronym, the WIM is one of the most significant structures in the known universe. It is estimated to contain somewhere between 40 and 50% of all the ordinary matter that exists, the baryonic matter, the protons and neutrons, the stuff that makes up atoms and therefore everything we've ever touched or seen. The WIM doesn't form uniform sheets or simple clouds. It traces the large-scale structure of the universe itself, following the filaments of dark matter that form the cosmic web, those immense thread-like structures that connect galaxy clusters across hundreds of millions of light-years. The WIM fills these filaments, stretched across cosmic distances in strands of hot, sparse plasma containing somewhere between 1 and 10 particles per cubic meter. Thin beyond imagination. Hot beyond anything we experience on Earth. Vast beyond any scale our intuition was designed to handle. The fact that ordinary matter, the same kind of matter you and everything around you is made of, is spread so thinly across such enormous structures is worth sitting with for a moment. We tend to think of matter as the solid, tangible, present thing. The substance of reality. And it is. But most of it, the majority of the ordinary matter in the entire universe, exists not in galaxies or stars or planets, but in this invisible, searingly hot plasma threaded between the galaxies like an immense glowing web. Before galaxies existed, this material was the universe. In the early epochs following the Big Bang, before gravity had gathered matter into stars, the intergalactic medium was essentially everything, a hot, expanding sea of hydrogen and helium plasma, slowly cooling, slowly structuring, slowly giving rise to the first knots of density that would eventually become the first galaxies. and the relationship between that intergalactic medium and the galaxies that formed within it has never really ended. Galaxies don't exist in isolation from the gas around them. They draw from it and they give back to it, in a long, slow exchange that continues across billions of years. When a galaxy needs fresh fuel for star formation, new hydrogen gas to collapse into new stars, it draws that material inward from the surrounding intergalactic medium. The gas falls in long filaments, cools, condenses, and eventually becomes part of a new generation of stars. And when those galaxies are active, when their stars are exploding and their central black holes are churning out energy, they push material back out. Galactic winds, outflows of gas and radiation, carry enriched material beyond the galaxy's boundaries and back into the surrounding medium. The intergalactic medium acts as both a reservoir and a recipient, a source of raw material flowing in, and a destination for enriched material flowing out. It breathes. Not in any biological sense, of course, but in terms of the long cyclic exchange of matter between galaxies and the space around them, there is something almost rhythmic about it. Matter falling inward over billions of years, stars forming, living, dying, blasting their products outward again. A cycle operating on timescales so vast that the entire history of human civilization wouldn't register as a single heartbeat within it. The universe is not the cold, static, empty darkness it appears to be from the inside. It is a dynamic, charged, searingly hot, endlessly exchanging system of matter and energy. And most of that system, most of the ordinary matter that the universe contains, is invisible to our eyes, threaded between the galaxies in glowing filaments of plasma, quietly making up the majority of everything, completely unknown to most of the people who live within it. Gravity is patient. It doesn't rush. It doesn't announce itself. It simply pulls, steadily and without interruption, across every distance and through every era of cosmic time. And given enough time, billions upon billions of years, even the most diffuse and evenly spread material in the universe will begin to respond to it, gathering, clustering, flowing slowly toward wherever the greatest mass happens to lie. The result of all that patient pulling is the structure we see when we map the universe at its largest scales. Not a uniform fog. Not a smooth sea of evenly distributed matter. But something far more textured and surprising, a vast network of filaments and walls and clusters and voids, a structure so immense and so intricate that astronomers named it the cosmic web. The intergalactic medium, for all its extraordinary scale and temperature, is not smooth. It is clumpy. It moves. Different regions have different densities, different temperatures, different histories. And under the continuous influence of gravity, the gas in the intergalactic medium flows, slowly, on timescales of hundreds of millions of years, toward the concentrations of mass that anchor the cosmic web. The motion is called peculiar motion, meaning motion that goes beyond the simple expansion of the universe, motion driven by the gravitational pull of structure. The intergalactic medium is not just sitting still between galaxies. It is drifting, flowing, being shaped by the same gravitational forces that built everything we can see. Within this structure, astronomers have found something unexpected. Scattered through the intergalactic medium, in regions where no galaxy currently exists, are giant clouds of atomic hydrogen. Vast, diffuse reservoirs of gas floating in the spaces between galaxies, unattached to any visible stellar system. They are not nothing. They are not remnants of something destroyed. Some of them appear to be something in the process of becoming. Certain of these hydrogen clouds have a distinctive shape, flattened, extended, something like a pancake spread across enormous distances. These structures are thought by some astronomers to represent the early stages of large-scale cosmic organization. Material that is in the slow process of collapsing and condensing, not yet into individual galaxies but into the larger groupings, the clusters and superclusters, that will eventually define this region of the universe millions or billions of years from now. The universe, in other words, is still assembling itself. The construction is ongoing. The chemical story of the intergalactic medium has also grown richer as our instruments have grown more sensitive. Oxygen, the third most abundant element in the universe and one absolutely essential to the chemistry of life, has been detected in the WIM in the form of highly ionized oxygen, specifically a state called oxygen 6, where an oxygen atom has been stripped of 5 of its 8 electrons by the intense heat of the surrounding plasma. This detection matters because it confirms that the enrichment of the intergalactic medium is real and measurable, that the heavy elements forged in stars and expelled by galaxies have genuinely made their way out into the spaces between galaxies and are present even in the most diffuse and remote regions of ordinary matter. The method of detection itself is worth pausing on. Astronomers found this ionized oxygen not by observing it emit light, but by observing it absorb light, specifically ultraviolet light from distant quasars passing through the WIM on its long journey toward our telescopes. The same principle that reveals the chemical composition of the intergalactic medium through quasar spectra applies here. The oxygen leaves its fingerprint on the light passing through it, and with sensitive enough instruments, we can read that fingerprint. X-ray observations have added further confirmation. The hot plasma of the WIM, heated to millions of degrees, both emits and absorbs X-rays in ways that carry information about its density and composition. By comparing what X-ray telescopes detect with what theoretical models predict, astronomers have been able to account for a significant portion of that long-missing ordinary matter, the baryons that simulations said should be out there but that earlier observations had failed to find. The WIM, slowly and painstakingly, is giving up its secrets. Meanwhile, the intergalactic medium has another remarkable property that speaks to just how thin and diffuse it truly is. The universe is constantly being crossed by cosmic rays, high-energy particles, mostly protons, accelerated to extraordinary velocities by some of the most violent events in the cosmos. Supernova explosions, the jets of active black holes, the shock waves of colliding galaxy clusters. These particles travel across the universe at close to the speed of light, and for the most part, the intergalactic medium does almost nothing to stop them. It is essentially transparent to cosmic rays, so sparse that even a particle traveling billions of light years will rarely encounter anything to deflect or absorb it. There is an exception. At the very highest energies, particles carrying more energy than almost any other in the universe, interactions with the diffuse photons of the cosmic microwave background radiation begin to limit how far they can travel. Even at that scale, the effect is subtle. But it represents one of the few ways in which the thinness of the intergalactic medium has measurable limits, and it tells us something about the ultimate sources of the most energetic particles we detect. Now, beyond the quiet physics of diffuse gas and drifting dust, there are objects within the universe that interact with the intergalactic medium in dramatically less subtle ways. Supermassive black holes, the engines at the centers of the largest and most active galaxies, don't just consume material. In doing so, they release staggering amounts of energy, and in many cases they drive enormous jets of plasma outward from the galaxy at relativistic speeds. These jets, sometimes extending for millions of light-years beyond the galaxy itself, plow into the surrounding intergalactic medium, heating it, compressing it, displacing it, and fundamentally altering the environment around the galaxy for vast distances in every direction. A single active supermassive black hole can influence the intergalactic medium across scales that dwarf any individual galaxy. The plasma it expels carries energy and magnetic fields far out into the cosmic web, stirring the intergalactic medium and leaving behind structures, radiolobes, giant bubbles of hot gas, that persist for hundreds of millions of years after the black hole quiets down. The most powerful objects in the universe are not isolated. They reach outward, shaping the medium that surrounds them, leaving their mark on the large-scale structure of the cosmos. And then there are the gravitational mysteries. The universe contains not just visible structures but anomalies, regions where the gravitational landscape is so unusual that it reshapes the motion of everything around it across enormous distances. One of the most striking of these is something astronomers call the Great Attractor. It lies in the direction of the constellation Centaurus, roughly 150 to 250 million light-years away, and it exerts a gravitational pull so significant that it is drawing our own galaxy, along with hundreds of other galaxies in our local region of the universe, toward it at hundreds of kilometers per second. What exactly the Great Attractor is remains partially obscured from us, because it lies behind the plane of the Milky Way, a region cluttered with the dust and gas of our own galaxy, which makes direct observation difficult. What astronomers can say is that it represents an enormous concentration of mass, likely a massive supercluster of galaxies, whose gravitational influence extends across a region of space almost beyond conception. We are moving toward it right now, and have been for billions of years. At the other extreme are the voids. If the cosmic web is defined by its filaments and clusters, it is equally defined by the enormous empty regions between them. The Boötes void is one of the most famous and striking of these, a roughly spherical region of space approximately 330 million light-years across, containing almost nothing. Where a region that size might be expected to contain thousands of galaxies, the Boötes void contains only a handful. It is not completely empty, but it is so dramatically underdense compared to the surrounding universe that it stands out as one of the largest coherent structures ever identified. The existence of voids like Boötes tells us something important about how the cosmic web formed. Matter, drawn by gravity toward the densest regions, has drained away from the voids over billions of years, leaving behind these vast, echoing empty spaces. The voids are the negative space of the universe's architecture, the emptiness that defines the shape of the structure around it, the way silence defines the shape of music. Together, the filaments, the walls, the clusters, the voids, the drifting hydrogen clouds, the X-ray emitting plasma, the black hole jets stirring the medium across millions of light years, all of it composes a single coherent structure. The largest structure in existence. A web stretching across the entire observable universe, built by gravity over billions of years, still being built right now, still shifting and flowing and assembling itself in ways that will take billions more years to complete. We live inside it, on a small rocky planet, in an ordinary galaxy, in one small corner of a filament, in one small region of a web so large that the mind can only approach its edges before quietly stepping back. And yet, slowly, and with great care, we are learning to read it. There's a kind of travel that requires no road, no medium, no vessel of any kind. A kind of movement that proceeds through the apparent emptiness of space with perfect indifference to the distances involved. Right now, at this moment, the space around you, around this planet, through this solar system, across the galaxy and beyond, is filled with travelers of this kind. Particles and waves and fields, streaming in every direction, crossing billions of light years, carrying information about events that happened before the Earth existed. Most of them pass through you without your knowledge. Some have been traveling since the first moments of the universe. None of them are stopping. Cosmic rays are among the most energetic of these travelers. Despite the name, they are not rays in the way that light is a ray. They are particles, mostly protons, the positively charged cores of hydrogen atoms, but also heavier atomic nuclei and occasionally electrons, accelerated to extraordinary velocities by some of the most violent processes in the cosmos. Supernova explosions, the rotating magnetic fields around neutron stars, the relativistic jets of matter fired outward by supermassive black holes. These events act as natural particle accelerators of a scale no human engineering has ever approached, flinging particles outward into the universe at speeds that approach the absolute limit of the speed of light. These particles travel through the intergalactic medium with remarkable freedom. The thinness of the medium, which we've already explored, means that cosmic ray particles can cross truly enormous distances without encountering anything to stop them. They arrive at Earth from every direction, streaming down through our atmosphere, where they collide with air molecules and produce cascades of secondary particles that rain down to the surface. Every second of every day, cosmic rays are passing through you. They have been doing so for your entire life, for the entire history of life on Earth, for the entire history of the planet itself. The vast majority of cosmic rays are made of ordinary matter, protons, atomic nuclei. But a small fraction, roughly 1/100%, are something rarer. They are antimatter. Specifically, positrons, the antimatter counterpart of the electron, and antiprotons. These antiparticles are produced in the violent interactions that generate cosmic rays, and while they are extraordinarily rare compared to their matter counterparts, their presence in cosmic rays is measurable and carries scientific significance. The ratio of matter to antimatter in cosmic rays reflects something about the environments and processes that produce them, and studying that ratio helps astronomers piece together the story of where the most energetic cosmic rays originate. But cosmic rays, for all their energy and significance, are not the most numerous travelers filling the space around us. That distinction belongs to something far more ghostly. Neutrinos are among the strangest and most abundant particles in the universe. They have almost no mass, so little that for decades physicists believed they had none at all. They carry no electric charge. They interact with ordinary matter only through the weak nuclear force, one of the fundamental forces of nature, and through gravity. In practical terms, this means a neutrino can pass through a light year of solid lead with only a marginal chance of interacting with anything along the way. They move through matter as if it simply weren't there. Every second, approximately 65 billion neutrinos from the Sun alone pass through every square centimeter of your body. They arrive from one direction during the day, passing through the Earth as if it were transparent, and arrive from the other direction at night, having traveled through the entire planet without noticing it. The Earth, to a neutrino, is less substantial than a thin morning mist. But the neutrinos generated by the Sun are only a small fraction of the total. The universe is permeated by neutrinos from every source imaginable: supernovae, active galactic nuclei, cosmic ray collisions in the atmosphere. And underlying all of them, forming a background so ancient it predates everything else we've discussed, are the relic neutrinos from the Big Bang itself. In the first second of the universe's existence, neutrinos were everywhere, in thermal equilibrium with all other particles, part of the hot, dense sea of matter and energy that filled all of space. As the universe expanded and cooled, those neutrinos decoupled from everything else, streaming freely outward in all directions, carrying a snapshot of the universe as it was nearly 14 billion years ago. Those neutrinos are still here. They fill every cubic centimeter of space, including the space inside this room, the space inside your body, the space between your atoms. The cosmic neutrino background is the oldest relic of the Big Bang that we can, at least in principle, detect, though in practice, their incredibly low energies make direct detection extraordinarily challenging. We are bathed, always and continuously, in the afterglow of the universe's first moments. The electromagnetic story of space is equally pervasive. Throughout the cosmos, electric and magnetic fields extend across every scale, from the microscopic fields around individual charged particles, to the vast magnetic fields that thread through galaxies, to the intergalactic magnetic fields that permeate the space between galaxies across hundreds of millions of light years. These fields are not incidental features of the universe. They are fundamental to how it works. The interplay between electric and magnetic fields is what gives rise to electromagnetic radiation, light, in all its forms. An oscillating electric field generates a magnetic field, and an oscillating magnetic field generates an electric field. These two fields sustain each other as they propagate outward through space, requiring no medium to travel through, carrying energy across the universe at the speed of light. This is why light, and radio waves, and X-rays, and gamma rays, and every other form of electromagnetic radiation can travel through the vacuum of space. They are not waves in a physical medium the way sound is a wave in air. They are waves in the electromagnetic field itself, self-sustaining, self-propagating, needing nothing to support them except the fundamental structure of space. Radio waves from the first radio broadcasts on Earth are now a sphere of electromagnetic radiation expanding outward through space at the speed of light, currently more than 100 light-years across, carrying fragments of human history into the galaxy. The light from a star 1,000 light-years away was produced 1,000 years ago and has been traveling toward us ever since. When we look up at the night sky, we are looking into the past, at light that left its source long before it arrived here, each photon having crossed an enormous distance to reach us. Space is full of this light, not just the visible wavelengths our eyes detect, but the full electromagnetic spectrum. X-rays and gamma rays, the most energetic forms, are produced in some of the most violent environments in the universe, the regions near neutron stars and black holes, the shock waves of supernova remnants, the jets of active galactic nuclei. These high-energy photons stream through space largely unimpeded by the intergalactic medium, arriving at our telescopes with information about processes so extreme that nothing remotely like them exists anywhere in our solar system. The intergalactic magnetic fields, while extraordinarily weak by everyday standards, have a measurable effect on the propagation of very high-energy cosmic rays. A charged particle moving through a magnetic field experiences a force that curves its path, and even fields as weak as those found in intergalactic space can deflect the trajectories of cosmic rays over the enormous distances they travel. This deflection is part of why tracing cosmic rays back to their sources is so difficult. They arrive at Earth from a direction that may not reflect where they originated. There is something quietly extraordinary about all of this. The universe that appears dark and empty when we look up is, in physical reality, saturated with information and energy. Cosmic rays streaming in every direction. Neutrinos from the Big Bang passing through everything without pause. Electromagnetic fields extending across intergalactic distances. X-rays and gamma rays carrying news of the most violent events in the cosmos. Radio waves propagating outward from every source that has ever transmitted them. The vacuum of space is not a passive backdrop. It is an active, dynamic medium, or rather, it is the stage upon which fields and particles and radiation perform a continuous and extraordinarily complex exchange of energy and information, operating at every scale simultaneously, from the quantum to the cosmic. We sit at the center of it, receiving these signals from every direction, from every distance, from every era of cosmic history. Most of them we cannot detect with our bodies. But with our instruments, slowly and with great ingenuity, we are learning to listen to all of them at once. And what they tell us about the universe, its age, its structure, its history, its composition, is a story that grows richer and more detailed with every passing year. There is a temperature to the universe. Not the temperature of a star, or a planet, or any object within it, but a background temperature that belongs to space itself. A faint, residual warmth spread with extraordinary uniformity across the entire observable cosmos, in every direction, at every point. If you could somehow remove every star, every galaxy, every particle of gas and dust, and measure the temperature of what remained, you would not find absolute zero. You would find something just slightly above it. A whisper of heat left over from something that happened nearly 14 billion years ago. That temperature is approximately minus 270.45 degrees Celsius. just 2.7 degrees above the coldest temperature that physics permits. Cold beyond anything that occurs naturally on Earth's surface, cold enough to freeze every gas we know of into solid form. And yet, in the context of the universe's history, this faint warmth is a remnant, the last detectable echo of an event of almost incomprehensible energy and heat. We call that echo the cosmic microwave background. And of all the things that fill the space between stars and galaxies, it may be the most significant. To understand what the CMB is, it helps to think about what the early universe was like. In its first moments, the universe was not the dark, cold, expansive place we inhabit today. It was a state of almost unimaginable density and temperature, a hot, opaque plasma in which matter and energy were so thoroughly intermingled that light could not travel freely. Photons, particles of light, were constantly being scattered by the dense sea of charged particles surrounding them. The early universe was, in this sense, like the interior of a star, brilliantly energetic, but completely opaque. Light was trapped. This continued for a surprisingly long time. For roughly 380,000 years after the Big Bang, the universe remained in this state, expanding and cooling, but still too hot and dense for neutral atoms to form. Then, at a moment astronomers call recombination, the temperature dropped to the point where electrons could finally settle into stable orbits around atomic nuclei. Hydrogen atoms formed for the first time. And with the formation of neutral atoms, the universe became, almost suddenly, transparent. Light that had been trapped, scattered endlessly in every direction, was suddenly free to travel. It streamed outward through the newly transparent universe in all directions, carrying with it information about the conditions at that precise moment in cosmic history. That light has been traveling ever since. It has been traveling for nearly 14 billion years. And it is still arriving at Earth today, from every direction simultaneously. It arrives not as visible light. In the time since it was released, the expansion of the universe has stretched its wavelengths enormously, from the infrared light it was when first released, all the way down to microwave radiation, the same general range of wavelengths used by microwave ovens, though at a vastly lower intensity. It fills all of space uniformly, at that characteristic temperature of 2.7 degrees above absolute zero. It is, in the most literal sense possible, the light of the universe's first transparent moment, still reaching us, still carrying its ancient message. The discovery of the CMB is one of the great stories of accidental science. In 1965, two physicists at Bell Labs in New Jersey, Arno Penzias and Robert Wilson, were working with a large horn-shaped radio antenna, attempting to make precise measurements of radio signals. They kept detecting an annoying background noise in their instrument, a persistent, uniform hiss that seemed to come from every direction equally, regardless of where they pointed the antenna. They checked everything. They looked for sources of interference. They famously cleaned pigeon droppings from the antenna, suspecting that contamination might be causing the problem. The noise remained. It was coming from the sky itself, from every point in the sky simultaneously. When Penzias and Wilson learned that a team at Princeton had been theoretically predicting exactly this kind of background radiation as a consequence of the Big Bang, the realization of what they had found was extraordinary. They had accidentally detected the oldest light in the universe. The discovery earned them the Nobel Prize in Physics in 1978. NASA once described the CMB as the first baby picture of the universe, and the description is apt in a way that rewards thinking about. When we look at the CMB, we are not seeing a reconstruction or a simulation. We are seeing actual light, actual photons, that were released when the universe was 380,000 years old. In an era when the universe is nearly 14 billion years old, that is vanishingly young. We are looking at the universe in its infancy, directly, with instruments sensitive enough to detect the faint temperature variations that were present in that ancient light. And those variations matter enormously. The CMB is not perfectly uniform. Across its vast surface, what astronomers call the last scattering surface, there are tiny temperature fluctuations, variations of about 1 part in 100,000. Regions that were very slightly hotter than average, and regions that were very slightly cooler. These fluctuations are not noise or measurement error. They are real, and they are crucial. Those tiny variations in temperature correspond to tiny variations in density in the early universe, regions where matter was ever so slightly more concentrated than its surroundings. And those slight overdensities were the seeds of everything that came after. Under the influence of gravity, the denser regions attracted more matter, grew denser still, and eventually became the first structures, the first galaxies, the first clusters, the filaments of the cosmic web. The entire large-scale structure of the universe today can be traced back to those minuscule ripples in the CMB. Where did those ripples come from? The leading explanation takes us back even further, to a period in the universe's earliest moments called inflation, a hypothesized period of extraordinarily rapid expansion in which the universe grew from something smaller than an atomic nucleus to a scale many times larger in an almost incomprehensibly brief instant. During inflation, quantum fluctuations, the inherent, irreducible randomness of the quantum world, were stretched to macroscopic scales by that expansion. What were quantum scale variations became cosmic scale density variations. The seeds of galaxies were written into the universe by the laws of quantum mechanics, operating at the smallest conceivable scales, and then inflated to cosmic proportions. The universe we live in, with its galaxies and filaments and clusters and voids, is, in a deep sense, the amplified image of quantum randomness in the universe's first fraction of a second. The CMB has also revealed something else, something that continues to generate scientific discussion and careful study. The temperature fluctuations in the CMB, when mapped with extraordinary precision by satellites like WMAP and Planck, show a pattern that is not quite perfectly symmetric. There appear to be subtle differences between one hemisphere of the CMB and the other, what some researchers have called the axis of evil, a somewhat dramatic name for a statistical anomaly in what should, according to the simplest models, be a uniformly random pattern. Whether this asymmetry represents a genuine departure from perfect cosmological symmetry, a hint at some physics we don't yet understand, or simply a statistical artifact, is a question that remains genuinely open. Some researchers have proposed that it might indicate something about the shape or topology of the universe at scales larger than we can observe. Others interpret it more cautiously. It is one of several features of the CMB that continue to motivate research and debate. What is not in doubt is that the universe is expanding. The same expansion that has stretched the CMB photons to microwave wavelengths over 14 billion years is continuing right now. Every galaxy not gravitationally bound to our local group is moving away from us, and the further away it is, the faster it recedes. Space itself is growing. The observable universe, the sphere of space from which light has had time to reach us, has a finite radius, but it sits within a larger universe of unknown extent that continues to expand beyond what we can ever see. The CMB sits at the edge of what we can observe, not in space, but in time. It is the oldest light we can detect, the furthest back we can see with electromagnetic radiation. What lies beyond it, in the opaque plasma of the universe's first 380,000 years, is accessible only through inference and theory, and through other messengers, gravitational waves, perhaps, or the relic neutrinos we discussed earlier. But the CMB itself, faint and ancient and everywhere at once, is one of the most profound things in the universe. It is the universe's memory of its own beginning. A whisper from the moment when everything we know became, for the first time, possible. We have spent some time now exploring what fills the universe, the gas, the dust, the plasma, the radiation, the ancient light still echoing from the moment of creation. And in doing so, we have been talking, without quite saying so, about a remarkably small fraction of everything that exists. All of it, every atom of hydrogen drifting in the interstellar medium, every grain of cosmic dust, every star that has ever burned, every planet that has ever formed, every galaxy we have ever mapped, every particle we have ever detected, all of the ordinary matter in the entire observable universe amounts to roughly 5% of its total content. 4.9%, to be more precise. The remaining 95% is something else entirely. This is not a small uncertainty, or a gap at the edges of our knowledge that future instruments might fill in. It is a fundamental feature of the universe as we currently understand it. The matter we can see, the matter we can touch and measure and detect with every instrument we have ever built, is a minority component. A thin visible layer floating on top of something vast, dark, and still largely mysterious. The larger of these two unknowns, the one we call dark matter, accounts for approximately 27% of the universe's total energy content. That makes it roughly 5 times more abundant than ordinary matter. 5 times more of the universe is made of something we cannot see, cannot touch, and have never directly detected than is made of everything we have ever studied in the whole history of science. What we know about dark matter, we know almost entirely through its gravitational effects. Dark matter does not emit light. It does not absorb light. It does not interact with electromagnetic radiation of any kind, which is why it is invisible to every telescope that detects photons, and all telescopes detect photons, in one wavelength or another. It simply does not participate in the electromagnetic interaction. It is, in that sense, transparent to the entire spectrum of light. But it has mass. And mass produces gravity. And gravity affects the things we can see. The first strong evidence that something invisible was contributing to the gravitational dynamics of galaxies came from observations of how galaxies rotate. When astronomers measured the orbital velocities of stars at different distances from the centers of galaxies, they expected to find what we see in our own solar system, objects further from the center of mass moving more slowly, in accordance with the laws of gravity. Instead, they found that stars at the outer edges of galaxies were moving just as fast as stars closer in, or in some cases faster. The rotation curves were flat where they should have declined. The only explanation that fit the data was that there was additional mass present, mass that didn't show up in the visible light of the galaxy, distributed in a large halo extending well beyond the visible disk of stars. Something was there, gravitationally, that wasn't there optically. Dark matter. The evidence accumulated from multiple independent directions. The way light bends around massive galaxy clusters, a phenomenon called gravitational lensing, showed that clusters contained far more mass than their visible galaxies could account for. The large-scale structure of the universe, the very cosmic web we explored earlier, couldn't have formed the way it did without a dominant component of dark matter providing the gravitational scaffolding for ordinary matter to fall into. Simulations of cosmic structure formation only matched observations when dark matter was included. Without it, the universe as we know it simply wouldn't exist. And this brings us to one of the most significant things we understand about dark matter's role in cosmic history. It was first. Dark matter, unlike ordinary matter, doesn't interact with radiation. In the early universe, when ordinary matter was tightly coupled to the sea of photons, bouncing, scattering, unable to collapse freely under gravity, dark matter was already free. It had already begun to respond to gravity, already begun to clump and gather into the first subtle structures. While ordinary matter was trapped in the glowing plasma of the early universe, dark matter was quietly building the scaffolding. By the time ordinary matter decoupled from radiation at recombination, the moment we associate with the release of the CMB, the dark matter structures were already there, waiting. The first halos of dark matter had already formed, their gravitational wells already dug, ready to catch the ordinary matter that was now free to fall. Ordinary hydrogen and helium flowed into those pre-existing dark matter structures and began to cool and condense at their centers. That is where the first stars ignited. That is where the first galaxies took shape. Dark matter did not just coexist with ordinary matter in cosmic history. It preceded it, in the structural sense. It determined where galaxies would form before a single star had ever burned. It wrote the address of every galaxy in the universe into the gravitational landscape of space before ordinary matter had any say in the matter. The relationship between dark matter and ordinary matter is not incidental. It is foundational. Dark matter is the skeleton of the universe, and ordinary matter is the flesh that grew around it. Every galaxy we have ever seen exists where it does because a dark matter halo formed there first and created the gravitational conditions for a galaxy to be possible. Dark matter passes through ordinary matter essentially without interaction. If a dark matter particle and a proton were to occupy the same region of space, which is happening constantly, since dark matter permeates the galaxy including our own solar system, they would simply pass through each other. No collision. No deflection. No exchange of energy. The dark matter particle continues on its way as if the ordinary matter weren't there. This is what gives dark matter its ghost-like quality, not that it is insubstantial in a gravitational sense, but that it is completely invisible and intangible to everything except gravity. We move through a sea of dark matter every moment of our lives. Our bodies, the Earth, the entire solar system are embedded within a dark matter halo that extends far beyond the visible disk of the Milky Way. Dark matter is streaming through us right now, through the walls of this room, through the planet beneath our feet, through everything, and we cannot feel it, detect it, or interact with it in any way that our instruments have yet been able to measure. The search for direct detection of dark matter particles is one of the great experimental challenges of modern physics. Detectors have been built deep underground, shielded from the noise of cosmic rays and everyday radiation, designed to catch the extraordinarily rare occasions when a dark matter particle might interact with an ordinary atomic nucleus and produce a measurable signal. So far, despite enormous sensitivity, no confirmed direct detection has been made. The dark matter particles, if they interact with ordinary matter at all beyond gravity, do so with a frequency and energy that remains just below the threshold of what our instruments can currently detect. What we can do is map dark matter indirectly, through its gravitational effects on light. Gravitational lensing, the bending of light around massive concentrations of matter, works whether the mass is visible or not. By carefully analyzing the distorted shapes of background galaxies as their light passes through or around regions of space, astronomers can reconstruct the distribution of mass in those regions, including the dark matter component. The result is a map of something invisible, drawn in the curved and distorted light of distant galaxies. In recent years, the James Webb Space Telescope has produced what astronomers describe as the sharpest and most detailed dark matter maps ever made. The extraordinary resolution and sensitivity of Webb, combined with its ability to detect extremely faint and distant galaxies, has allowed gravitational lensing analyses of unprecedented precision. These maps reveal the distribution of dark matter within galaxy clusters in extraordinary detail: the clumps, the filaments, the dense cores and extended halos, with a clarity that previous telescopes couldn't approach. What those maps show is consistent with everything we've come to understand about dark matter's role in cosmic structure: a diffuse, extended distribution of invisible mass, clustered most densely where galaxies cluster most densely, tracing the same large-scale structure as the visible universe but extending well beyond it, in halos and filaments that reach into the darkness between galaxies. We have spent centuries believing that the matter we could see was, broadly speaking, the matter that existed. That the universe was made of the same stuff as us, operating by the same rules, accessible through the same instruments. The discovery of dark matter has permanently changed that understanding. We are, in the deepest sense, the minority. The visible universe, everything we have ever observed, measured, and named, is an island of ordinary matter floating in an ocean of something we don't yet understand. And remarkably, dark matter is only part of the mystery. Because there is still the remaining 68% of the universe's content to account for. Something even stranger. Something that doesn't just sit quietly like dark matter, shaping structure through gravity, but actively pushes the universe apart. That is a story for what comes next. We ended the last chapter with a promise that dark matter, for all its strangeness, was only part of the story. That after accounting for ordinary matter and dark matter together, there was still something left. Something larger than both. Something that makes up the single biggest component of the entire universe, and which we understand, in honest terms, barely at all. Dark energy. It accounts for 68.3% of the total energy content of the observable universe. Not a small correction. Not a marginal addition. The dominant ingredient. If the universe were a recipe, dark energy would be the majority of everything in it, with dark matter making up most of the rest, and ordinary matter, all the stars, all the galaxies, all the gas and dust and plasma and ancient light we have spent this entire journey exploring, accounting for less than 5% of the total. We live, it turns out, in a universe made mostly of things we do not understand. The story of dark energy begins with an expectation that turned out to be wrong. For most of the 20th century, cosmologists assumed that the expansion of the universe, which had been observed since the 1920s, must be slowing down. This seemed obvious and reasonable. The universe is full of matter, and matter has gravity, and gravity is attractive. The outward expansion set in motion by the Big Bang should, over time, be gradually braked by the mutual gravitational attraction of everything in the universe pulling on everything else. The only question was whether the universe would slow, stop, and eventually collapse back on itself, or whether it would slow and continue expanding forever, thinning out toward an eternal cold darkness. What nobody seriously expected was that the expansion might be speeding up. In 1998, two independent teams of astronomers studying distant Type Ia supernovae, a particular class of stellar explosion that can be used as a reliable cosmic distance marker, made a discovery that was, by any measure, one of the most startling in the history of science. The distant supernovae were fainter than expected. Not by much, but by a consistent and measurable amount. And the only explanation that fit was that those supernovae were further away than they should have been, that the universe's expansion, rather than slowing down as gravity demanded, was in fact accelerating. The universe is not just expanding. It is expanding faster and faster with every passing moment. Something is pushing space apart, overcoming the gravitational attraction of all the matter in the universe, driving the expansion to accelerate rather than slow. That something was named dark energy, and both teams of researchers who discovered it shared the Nobel Prize in Physics in 2011. The simplest and currently most widely accepted description of dark energy identifies it with the cosmological constant, a term Einstein himself introduced into his equations of general relativity, though he later dismissed as unnecessary. The cosmological constant represents a constant energy density that is an intrinsic property of space itself. Not energy stored in matter, not energy carried by particles or radiation, but energy that belongs to the vacuum, to empty space, as a fundamental quality of its existence. This is a profound and genuinely strange idea. In classical physics, empty space has no energy. It is simply the absence of things. But quantum mechanics tells a different story. The vacuum is not truly empty at the quantum level. It seethes with activity, with virtual particles flickering in and out of existence, with fluctuating quantum fields that carry a real and measurable energy. The cosmological constant, in one interpretation, is the energy of this quantum vacuum, expressed at the cosmic scale. If dark energy is indeed a property of space itself, then as the universe expands and space increases in volume, the total amount of dark energy increases proportionally. More space means more dark energy, which drives faster expansion, which creates more space, which creates more dark energy. The acceleration is self-reinforcing. And because dark energy's density remains constant as space expands, unlike matter, which becomes more dilute as the volume it occupies grows, dark energy becomes increasingly dominant over time. In the early universe, matter and radiation dominated. Now, dark energy dominates. And in the future, it will dominate more completely still. The effect of dark energy on structure formation is the inverse of dark matter's effect. Where dark matter pulls matter together, clustering it, building halos and filaments in the scaffolding of the cosmic web, dark energy pushes things apart. It acts, as cosmologists sometimes describe it, like a kind of anti-gravity, not a force that repels matter in the way that like magnetic poles repel each other, but a property of space that causes the space between things to grow, driving everything apart on the largest scales. On small scales, within galaxies, within galaxy clusters, within gravitationally bound systems, dark energy has little effect. Gravity, over short distances, is still dominant. Our solar system is in no danger of being pulled apart by dark energy. The Milky Way is not about to disperse. But on the scales of hundreds of millions of light years and beyond, dark energy wins. The distant clusters of galaxies are receding from us faster and faster, and given enough time, regions of the universe currently visible to us will eventually recede so fast that their light can no longer reach us. The observable universe, far in the future, will become smaller, not larger, as dark energy drives more and more of the cosmos beyond the reach of any possible observation. Dark energy acts, in this sense, as a brake on the largest scales of cosmic structure. While gravity works to cluster matter into filaments and nodes and clusters, dark energy works against that clustering at the grandest scales, limiting how large structures can grow, preventing the cosmic web from continuing to thicken and consolidate indefinitely. The tension between these two forces, gravity pulling inward, dark energy pushing outward, shapes the large-scale structure of the universe in ways cosmologists are still working to fully characterize. What dark energy actually is, at a fundamental level, remains one of the most important open questions in all of science. The cosmological constant is a description, a mathematical term that fits the observations, but it is not an explanation. When physicists attempt to calculate the energy of the quantum vacuum from first principles, using quantum field theory, the answer they get is enormously larger than the value of the cosmological constant actually observed. This discrepancy, sometimes called the worst prediction in the history of physics, suggests that something deep is missing from our understanding. Either the quantum vacuum doesn't contribute to dark energy in the way we expect, or there is some unknown mechanism that cancels out almost all of its energy, leaving only the tiny residual we observe. We don't know which, and we don't know why. Other proposals exist. Some physicists argue that dark energy is not a constant but a dynamic field, something that evolves over time, stronger or weaker at different epochs, potentially changing the universe's expansion rate in ways future observations might detect. This hypothetical field has been given various names, the most common being quintessence. If dark energy is quintessence rather than a true cosmological constant, its value in the past and future would differ from its value today, and with precise enough measurements, that difference might be detectable. Recent results from large-scale surveys of the universe have begun to hint, tentatively, that dark energy might not be perfectly constant, that its behavior might be subtly evolving with time. These results are preliminary and subject to ongoing scrutiny, but they represent exactly the kind of observational leverage that might eventually distinguish between competing theories. The next generation of surveys, mapping the positions and distances of billions of galaxies across cosmic time, are designed specifically to test whether dark energy is constant or dynamic. And so we find ourselves here, at the end of a journey that began with a simple question: what is space made of, and has led us, step by step, to the edges of what science currently knows. We started with the assumption that space was empty, and found that it was full of gas and dust and plasma and radiation and ancient light and cosmic rays and ghostly neutrinos streaming through everything without pausing. We found that the visible universe had a structure, a cosmic web of filaments and voids built by gravity over billions of years. We found that ordinary matter was only a fraction of what exists, that dark matter makes up 5 times as much and wrote the gravitational script that galaxies followed in forming. And we found that even dark matter was the minority, that the largest single component of the universe is something we have no direct detection of, something that appears to be a property of space itself, something that is actively accelerating the expansion of everything. Space is not empty. But it is also not what we expected. It is stranger than our intuitions, stranger than our earliest models, stranger in some ways than our current theories can fully explain. The 5% of the universe we understand with confidence is extraordinary enough. It gave us stars and planets and chemistry and life. The 95% we are still reaching toward may contain answers we cannot yet imagine. The question of what space is made of doesn't have a final answer. Not yet. But the act of asking it, of looking up and wondering what is really out there, what fills the darkness, what drives the expansion, what built the structure, what underlies everything, that act is one of the most human things there is. In the universe, patient and vast and quietly full of things we are only beginning to understand, continues to wait for us to find out. Science has a habit of revealing that the closer you look at something, the stranger it becomes. From a distance, space appears to be the simplest thing in the universe, the absence of things, the background against which everything else happens. But we have seen, over the course of this journey, that every layer of closer examination reveals new complexity. Gas and dust, plasma and radiation, dark matter and dark energy. And now, at the deepest level we are currently able to probe, something stranger still. Space and time, it turns out, are not separate things. This was one of Einstein's most profound contributions to human understanding. In the physics that preceded him, space was the stage and time was the clock, independent, absolute, unchanging. Space was where things happened, and time was when they happened, and the two had nothing essential to do with each other. Einstein showed that this picture was wrong. Space and time are woven together into a single four-dimensional fabric, which physicists call spacetime. They are not independent. What you measure as distance depends on how you are moving. What you measure as time depends on where you are and how fast you are traveling. Space and time are aspects of the same underlying structure, and that structure is dynamic. It can change, it can curve, it can respond to the presence of mass and energy. This is the central insight of general relativity. Mass doesn't just sit in space, it warps the spacetime around it. A massive object like the sun bends the fabric of spacetime in its vicinity, and what we experience as the gravitational attraction between objects is really the effect of that curved spacetime on the paths that everything, including light, must follow through it. The planets don't orbit the sun because an invisible force reaches across space and pulls them. They follow the curves in spacetime that the sun's mass has created. The analogy of a heavy ball placed on a stretched rubber sheet, deforming its surface into a well, captures something of this idea, though like all analogies it has its limits. The actual geometry of curved spacetime is four-dimensional and described by the mathematics of differential geometry, equations that Einstein spent nearly a decade developing. But the core intuition holds: mass shapes space, and shaped space determines how mass moves. The two are in constant dialogue. If spacetime is a fabric, then disturbances in that fabric can propagate as waves. This was another of general relativity's predictions, one that Einstein himself was uncertain would ever be measurable, because the effect seemed so extraordinarily small. Gravitational waves are ripples in spacetime itself, produced when massive objects accelerate, most powerfully when two black holes or neutron stars spiral inward toward each other and merge. As they do, they send waves of compressed and stretched spacetime outward in all directions at the speed of light, passing through everything, distorting space itself by infinitesimal amounts as they go. In 2015, a century after Einstein's prediction, the LIGO detector, an instrument of almost incomprehensible precision, capable of measuring a distortion of spacetime smaller than 1,000th the diameter of a proton, detected gravitational waves for the first time. The signal lasted a fraction of a second. It was produced by two black holes merging more than 1 billion light-years away. And it confirmed, directly and undeniably, that spacetime is not a passive backdrop but a physical entity that can bend, stretch, and ripple. Gravitational waves pass through the Earth constantly. They pass through you as you listen to this. Most are too small to detect, produced by events too distant or too gentle. But they are there, spacetime itself, flexing in response to the motions of the universe's most massive objects, carrying information across billions of light-years about mergers and collisions that happened long before life arose on Earth. But the strangeness of space at its deepest level goes beyond even curved spacetime and gravitational waves. It goes all the way down to the quantum level, to the behavior of reality at the smallest scales we can probe, and what it reveals there is perhaps the most philosophically striking finding of all. Quantum field theory, the framework that underlies our understanding of particle physics, describes the universe not as a collection of particles moving through empty space, but as a collection of fields that permeate all of space. The electron field, the quark field, the photon field, which is the electromagnetic field quantized. These fields exist everywhere, at every point in the universe simultaneously. Particles, in this framework, are not fundamental objects, they are excitations of these fields. A photon is a ripple in the electromagnetic field. An electron is a ripple in the electron field. The particle-like behavior we observe is what happens when these fields are disturbed. And here is where it becomes deeply strange. Even in their lowest energy states, even when no particles are present, even in what we would call a vacuum, these quantum fields are not calm. They are not still. The uncertainty principle, one of the foundational results of quantum mechanics, prevents any field from having a perfectly defined, perfectly zero value at any point. There is always an irreducible quantum uncertainty, an inherent jitteriness that cannot be removed. The vacuum is not empty. It is filled with what physicists call quantum fluctuations, constant, unavoidable variations in field values that occur even when no particles are present. These fluctuations have real, measurable consequences. One of the most striking is the production of virtual particles. In the quantum vacuum, pairs of particles and their corresponding antiparticles, an electron and a positron, for example, can spontaneously appear out of the energy of the vacuum itself, exist briefly, and then annihilate each other and return their energy to the vacuum. These virtual particles are not merely theoretical constructs. Their effects are measurable. The Casimir effect, a tiny but real attractive force between two uncharged metal plates placed very close together in a vacuum, arises because the virtual particle fluctuations of the quantum vacuum are altered by the presence of the plates. The plates restrict which fluctuations can occur in the space between them, creating a slight imbalance in the radiation pressure on either side, and the plates are pushed together by this imbalance. The vacuum exerts a force. Empty space presses. This is not metaphor, it has been measured in laboratories. Alongside all these quantum fields, there is one that deserves special mention because of what it does and what it means for our understanding of the universe's fundamental structure. The Higgs field. Unlike most quantum fields, which are zero in their lowest energy state, the Higgs field has a non-zero value throughout all of space, even in a perfect vacuum. It permeates everything, everywhere, always. And the interaction of other particles with this ubiquitous Higgs field is what gives them their mass. An electron moving through space is, in a sense, continuously interacting with the Higgs field, and the resistance of that interaction is what we experience as the electron's mass. Without the Higgs field, particles would have no mass. They would all move at the speed of light. Atoms would be impossible. Chemistry would be impossible. Structure of any kind would be impossible. The Higgs field, confirmed experimentally with the detection of the Higgs boson at CERN in 2012, is not an exotic addition to the universe, it is one of its essential foundations. And it fills all of space, invisibly, continuously, making the existence of matter as we know it possible. The zero-point energy of the quantum vacuum, the irreducible minimum energy that quantum fields carry even in their ground state, is related to all of this. Every quantum field contributes to the vacuum's energy. The sum of these contributions is what physicists call the zero-point energy of space, and it is connected, theoretically, to the cosmological constant and dark energy we explored earlier. The difficulty, as we touched on before, is that naive calculations of the zero-point energy yield a value many orders of magnitude larger than the dark energy we actually observe. Some cancellation, some mechanism we don't yet understand, reduces the effective vacuum energy to its observed tiny value. This is one of the deepest unresolved problems in theoretical physics. And then there is an idea that sits at the frontier of current research, one that may connect the quantum nature of space to questions about information and computation in the universe. The suggestion that vacuum states in space can store information is related to developments in our understanding of black holes, entropy, and the holographic principle. In ways that physicists are still actively working out, the quantum state of a region of space, the precise configuration of all its quantum fields, may encode information in a way that has fundamental implications for how we think about the nature of reality itself. The details are genuinely at the edge of what is currently understood, and their full implications remain the subject of active theoretical work. What all of this converges toward is a single, unavoidable conclusion: space may never truly be empty. Not in the classical sense, not in the quantum sense, not at any level we have yet been able to probe. Remove all matter. Remove all radiation. Remove all detectable particles of every kind. What remains is not nothing. What remains is spacetime itself, a fabric that can curve and ripple and carry gravitational waves. What remains are quantum fields in their ground states, fluctuating with irreducible quantum uncertainty, producing virtual particles, exerting measurable forces, storing information. What remains is the Higgs field, pervading everything with its non-zero value, making the existence of mass possible even in the absence of any actual massive particles. What remains is the zero-point energy of the vacuum, the cosmological constant, the dark energy that is driving the expansion of the universe. The question we began with, what is space made of, has turned out to be one of the most generative questions in all of science. Every layer of the answer has revealed another layer beneath it. Every answer has carried within it a new question. And the deepest answer we currently have is not a satisfying final statement but an open door. Space is made of spacetime, which curves and carries waves. It is made of quantum fields that are never truly at rest. It is made of a Higgs field that gives matter its mass. It is made of vacuum energy whose ultimate nature we don't yet understand. And perhaps it is made of something we have no name for yet, some deeper structure that a future theory of quantum gravity will reveal, something that underlies both general relativity and quantum mechanics and resolves the tension between them. We do not have that theory yet, but we are working toward it. And now, as we near the end of this long and quiet journey through the nature of space, there is room for a few smaller wonders, the kind of facts that don't fit neatly into any grand theoretical framework, but which remind us that the universe has a personality as well as a structure. A fondness for the unexpected. A habit of being strange in ways that delight rather than confound. There are planets with no star. Rogue planets, worlds that formed in solar systems and were then ejected by gravitational interactions, sent wandering through the galaxy in perpetual darkness, untethered to any sun. And there are not a few of them. Current estimates suggest there may be something like 500 million rogue planets drifting through the Milky Way alone. Worlds of rock and perhaps ice, moving in silence through the darkness between stars, never seeing daylight, never warmed except perhaps by the residual heat of their own interiors. Some may even have subsurface oceans, kept liquid by geothermal energy deep below frozen surfaces, with no star in their sky at all. If you were ever to visit space, and astronauts have described this in interviews, you would notice something unexpected. A smell. Not during a spacewalk, where you are sealed in your suit, but when returning inside after one. A distinct and peculiar odor clings to spacesuits and equipment that have been exposed to the vacuum, something variously described as hot metal, seared steak, or welding fumes. The exact chemistry is still debated, but it appears to be related to high-energy particles and possibly polycyclic aromatic hydrocarbons interacting with suit materials. The vacuum of space, it turns out, has its own signature, detectable in the residue it leaves behind. Temperature in space is a complex concept, and the Boomerang Nebula demonstrates this beautifully. Located about 5,000 light-years from Earth, it is a young planetary nebula, the ejected outer layers of a dying star, and it holds the distinction of being the coldest known natural object in the universe. At approximately 1 degree above absolute zero, it is actually colder than the cosmic microwave background, which fills all of surrounding space at 2.7 degrees above absolute zero. It achieves this through a process of rapid expansion of its gas, which cools the material below even the background temperature of the universe. It is, in a sense, a natural refrigerator operating at a scale of light years. Among the strangest apparent paradoxes in observational astronomy is the existence of stars that appear, from certain measurements of their age, to be older than the universe itself. The star HD 140283, informally called Methuselah, has been estimated at somewhere around 14.5 billion years old, which sits uncomfortably close to, or slightly beyond, the universe's estimated age of 13.8 billion years. This is not a sign that the universe is younger than we think, or that the star is genuinely older. It is a reminder of how difficult precise stellar age measurements are, and that the uncertainties in both the stellar age estimate and the universe's age overlap enough to make this a matter of measurement precision rather than a genuine paradox. But it is a striking example of how even our most confident cosmological numbers carry uncertainties that matter. The Earth itself has a more intimate relationship with the solar system's dynamics than we usually appreciate. Our planet occasionally captures small asteroids into temporary orbital relationships, objects that are not quite moons in any permanent sense, but which are gravitationally caught by the Earth-Moon system for months or years at a time before eventually departing. These are sometimes called mini-moons, and they are extraordinarily difficult to detect because of their small size. Only a handful have been confirmed, but the implication is clear. The Earth is occasionally, briefly, a multi-moon world, acquiring and releasing small companions on timescales too short to notice without careful observation. Jupiter's moon Ganymede holds a unique distinction among the moons of the solar system. It is the largest moon of any planet, larger even than the planet Mercury, and it is the only moon known to generate its own magnetic field. As a consequence of this magnetic field interacting with Jupiter's enormously powerful magnetosphere, Ganymede has its own auroras. Ultraviolet observations by the Hubble Space Telescope have confirmed these auroras, making Ganymede the only moon in the solar system known to glow with its own magnetic light show, independent of its parent planet. And then there is Venus, our nearest planetary neighbor, similar in size to Earth, and in almost every other way a world of fascinating extremes. Venus rotates in the opposite direction to most planets in the solar system. If you could stand on its surface and see the sun through its crushing, opaque atmosphere, the sun would rise in the west and set in the east. The reason for this retrograde rotation is still debated. It may be the result of a massive collision early in the solar system's history, or it may be related to complex atmospheric tidal dynamics. Either way, Venus spins the wrong way, slowly, taking longer to rotate once on its axis than it does to orbit the Sun. Its atmosphere is the most extreme of any planet in the solar system. Venus is not the closest planet to the Sun. Mercury holds that position, but it is the hottest, by a very wide margin. Its thick atmosphere of carbon dioxide, with clouds of sulfuric acid and a surface pressure 90 times that of Earth's, creates a runaway greenhouse effect that drives surface temperatures to around 465 degrees Celsius. Hot enough to melt lead. Hot enough that any spacecraft that has landed on Venus has survived for only a matter of hours before the environment overwhelmed its systems. Venus is, in its way, a warning, a vivid demonstration of how dramatically atmospheric chemistry can alter the conditions on a planetary surface, and of how narrow the range of conditions required for a world like ours actually is. And with that, we find ourselves at the end of a very long journey through the nature of space. We began with the assumption of emptiness and arrived, by degrees, at one of the most densely fascinating landscapes imaginable. Space is not empty. It is full of gas and dust and plasma and radiation and fields and fluctuations and the stretched fabric of space-time and the invisible scaffolding of dark matter and the mysterious pressure of dark energy. It contains the oldest light in the universe and the quietest cold. It shelters wandering planets with no sun and moons that make their own auroras and nebulae colder than the background temperature of everything. The night sky above us is not a backdrop. It is a depth, an almost incomprehensible depth of structure and history and physics, much of it invisible, much of it still beyond our understanding, all of it quietly present whether we look up or not. And the question of what space is really made of, the question this journey began with, remains as alive as ever. Not because we haven't found answers, but because every answer has only deepened the question. That, perhaps, is the most honest and most beautiful thing we can say about it. The universe is stranger than it appears. And that strangeness is an invitation to keep asking, keep looking, and keep finding that the darkness above us is full of things we have not yet learned to see.